Good morning, everybody. Today, we're presenting a data structure project, an electronic stock trading platform in C++.
So this is a real-time exchange system powered by heaps and hash maps, capable of matching 40,000 order per second.
By the end of this demo, we'll explain why we chose the data structures we did, why we chose heap for price priority for free, justify our O log of n insert and delete times, and relate it to the hash map O of 1 to cancel the operations.
So what's the challenge? Imagine handling 40,000 orders flooding in every single second. Each one must obey three strict rules.
Three rules. First, price priority. The better prices get matched first. Second, time priority. If two orders have the same price, whoever arrived first gets it. Third, partial fill. If an order is too large, we match part of it and keep the rest active.
Yeah, so the question is, how do we handle this massive flow efficiently while obeying all these rules? That's where our data structure comes in.
So we chose four main structures, each for a very specific reason. For buy orders, we use a max heap using STL's priority queue, which gives us an O log of n insertion.
For sell orders, we use a min heap. Also priority queue with a complexity of big O log and insertion. Let me quickly refresh the heap property.
As you can see, in the max heap, every parent is greater than or equal to the children. In a min heap, it's the opposite. We use the array index trick where the parent of an index I is at I minus 1 by 2.
So here's a quiz section. Where's the largest buy order in our max heap?
At the root, index 0. And that's the
Exactly.
beauty of it. The best price is always instantly accessible at the top.
Third, third structure, an unordered map for order lookup, giving us a time complexity of big O1, average time to find any order. And fourth, a vector for trade history with log O1 push operations.
Here's where the magic happens. This C++ struct turns the STL's max heap into a max price heap with time priority baked in.
Notice the comparator checks price first. If price are equal, it compares timestamps. Earlier timestamps win. The key highlight is that we invert the natural order to turn STL max heap into a max price heap.
That's how we get both price priority and time priority automatically without writing any complex kind of sorting logic. Now, the matching engine.
Now, the heart of a system. The pseudocode is beautifully simple. We loop while both heaps have ordered, grab the top buy and top sell. And if the buy price is greater than or equal to the sell price, we execute a trade.
For the trade price, we follow a very simple rule. The price whenever the price is equal, whichever order arrives first. So if sell at 50 arrives at 9001, 9 o'clock and 1 millisecond, and a buy order 55 arrives at 9 o'clock and 3 seconds, the trade would execute at $50.
Yeah. So let me show you the time priority in action. Say we have three buy order, all at $100. One at timestamp 10, one at 11, and the another one at 12. When a $100 sell arrives, who trades first?
The earliest, the one at the timestamp 10, the one at the timestamp at 10. Or he would automatically handle this through the comparator.
Now for partial fill, step 1. A buys for 150 shares at $100 enters. Step 2. A sell for only 60 shares at $100 arrives. Step 3. We trade 60 shares and all the remaining 90 shares by order get pushed back into the heap.
As you can see, these three are very important and they're very interlinked with each other. And crucially, this remains O log of n complexity with no efficiency loss.
Okay, so for cancellation, we use an unordered map storing order ID to order pointer. This gives us the time complexity of big O1 average time for finding and cancelling the orders.
The key is storing the pointers and not the copies. The key is storing the pointers and not the copies. This would maintain the iterator stability. When we modify an order, the change reflects everywhere.
Okay, so let me summarize our performance insert order complexity of big O login, match and pop, again, big O login, cancel. Memory per order is roughly 64 bytes.
Compare this to an array. O of n insertion, O of n searching. Our approach is exponentially faster for much larger order volumes, and it scales much better that way as well.
Okay, so here's actual output from a CPP program running live. You can see trade executions with price, quantity, buyer, and seller information.
We built a completely interactive system where users can run demo cases manually. They can place orders. They can view the current order book showing to top bids, ask, and check the recent trade history and see the platform statistics that are present.
Okay, so what we learned first, heaps gives price priority without extra code. It's built into the structure. Second, custom comparators make time type breaking trivial. Third, hash maps plus pointers give us safe time complexity access.
The O of on access is what it gives. And here's the incredible part: real exchanges like the Nasdaq use exactly identical logic. It's just implemented in a FPGA chip at the hardware level for microsecond speed.
Abstract data from our textbook literally move trillion of dollars every day.
We ran our code through a plagiarism checker. It only got 11%, which is way below the acceptable, which is way below the 15% acceptable limit. The small similarity is just standards, library functions, common syntax. Our implementation is entirely original.
And our reference include Commons Chapter 6 on heaps and the NASDAQ IDCS specification for the real world protocols.
We're happy to answer any questions with regards to this about our design decisions, our complexity analysis, or our implementation as such.
So, guys, I have a question for you. What happens if two traders place orders at the same time and at the same price? How does the system handle that?
Yeah, so I would like to answer a question. Actually, in practice, timestamps include nanosecond, making simulations order extremely rare. If truly simultaneously order add increment counter become the tiebreaker, system design ensures deterministic behavior.
Okay, so you mentioned about FPGA implementation. Can you explain what advantages that provides over a software implementation like the C++ code we see here?
Excellent question. So the FPA would execute at a hardware level, like 100 to 500 nanoseconds versus the milliseconds that we are getting. There is no operating system overhead, no garbage collection, no context switching. It can also allow for parallel processing, which can handle multiple different requests simultaneously. It is mostly used in like professional setting, high frequency trading, within where microsecond operations matter.
I also have one more
Okay,
question for you. What happens during a market crash when thousands of sell orders flood the system at once? How does the platform handle that load?
The priority structure queue would scale the priority queue structure would scale extremely well. It is O log of in complexity. Even with millions of orders, it's better than using an O of n array. There are circuit breakers in real-time exchanges, which would pause trading during very extreme volatility. We can have load balancing across multiple different matching engines and order throttling or rate limiting for it to make sure it doesn't become too overwhelming for the system.
okay, so that's it. Uh,
Thank you.
Thank you.
okay, so hello everyone, and welcome to our project presentation on Spatial Data Index and Nearest Neighbor Search. My name is Vansh Kataria.
And I am Malhar Kausadikar. For our data structures I, we are demonstrating a real-world implementation of this concept using KD trees. So let's start with the core of the challenge. How do systems like Google Maps or Zomato instantly locate the nearest hospital or ATM or even a restaurant? The answer, as our slide says, lies in spatial data indexing. The brute force way would be to check your location against every other location in the database. With over 1 million points, this O of n complexity approach would cause laggy, unusable delays. The optimized solution and the one we have built uses spatial index. This lets us intelligently prune or ignore vast, irrelevant sections of the map, achieving a much faster logarithmic time complexity.
Okay, so this slide shows about real-world applications that we uses. This technology isn't just theoretical. It powers mission-critical systems we use every day. In navigations like Google Maps, it finds routes and nearby landmarks. In ride-hailing like Uber and Ola, it's what matches you with the closest driver in a real time. And in delivery services like Swiggy, it finds a nearby restaurant and helps optimize the delivery route. All these industries demand instant geographic results. And that's what our project explores.
Okay, so to build this, two fundamental data structures are in work in our project. So the first one is the KD tree. This is the star of our show. It's a binary tree that works in multiple dimensions. As the slide says, it works by alternating the axis. It splits the map by longitude and latitude, and then longitude again, and so on. The divide and conquer strategy is what gives us that O log n complexity search time. Secondly, we use the principles of linked lists. Every node in our KD tree has dynamically allocated in memory using malloc. This creates a chain of pointers, a left child and a right child, which links the tree together. This dynamic memory approach is very memory efficient and gives us the flexibility to build a tree of any size.
Okay, so in this slide, we'll talk about the data transfer. In this, our algorithm follows four key phases as shown on this slide. First, we load coordinates. We wrote code to either pass a geographic data from a CSV file or for testing generate thousands of synthetic random coordinates. Secondly, we build a KD tree. This is the second setup phase. Our code recursively finds the median point for each dimension and partitions the space, building a balanced tree for the fastest possible queries. And third, we execute the query. This is where the magic happens. Our search function traverses the tree and uses a distance-based pruning to rapidly eliminate entire branches of the tree that are too far away. And fourth, we return the results. The program outputs the kth nearest neighbors or all the points within the radius sorted by the distance and we store them in CSV file.
So our C implementation is structured around four core functions. The first one is the build KD tree function. This is a recursive function we just mentioned that constructs the balanced spatial tree from the dataset. The second is the find nearest neighbor function. This is the simplest query. It performs the proximity search with pruning to find the single closest point. The third is the find k nearest function. This function retrieves multiple neighbors. It uses a max heap data structure to efficiently keep track of the top k closest points. And fourth and the last is find in radius function. And finally, this function returns all points that fall within a specified distance from the query.
Okay, in this slide, we talk about a performance. So does it work? We ran rigorous benchmarks comparing our KD tree against the brute force method on a set of 1 million points. The results are clear. The brute force method took over 2.35 seconds to run a query, while our KD tree took only just 0.18 seconds. As you can see on this slide, there's 13 times speed up. This really shows the power of moving from a linear ON complexity to a logarithmic time complexity. So
Now to show a practical example, we ran a query for a real-world Mumbai coordinates, longitude 72.95 and latitude 19.10, and we asked it to find the nearest k equal to 5 neighbors. Now our program correctly processed this, performed the search, and saved the output to a CSV file named knresults.csv. Listing the five closest points and their exact distance, sorting from nearest to farthest.
So here are our key findings. So what are our key findings? The table summarizes perfectly. The time dropped from 2.35 seconds to just 0.18 seconds. The complexity improved from O and to logarithmic time complexity. And the scalability of the brute force is very poor. It gets slower with more points, but the KD tree has an excellent scalability. So in conclusion, special indexing with KD3 bridges the gap between classic data structures theory and the real-world application, allowing us to build a geographic queries what are truly real-time.
Now, finally, to ensure academic integrity, we ran our project through Turnitin. As the slide shows, we achieved a 15% similarity score, confirming our original implementation and analysis. Our work was built on foundations laid by computer scientists, primarily John Bentley's original 1975 paper on these trees, as well as resources like Geeks for Geeks and Introductions to Algorithms textbook. Now, Vansh, could you show us the Turnitin report?
Sure. Wait. So here is our Turnitin report. Here shows the similarity of 14%. Just so yeah, and this is our batch title of this. Yes, you can check it. We got a 14% of similarity, and for the code, this is our code. Here, we include all the libraries, required libraries, and here, for if you don't provide any CSV file input or anything else, it will create based on this data. Like the basic minimum longitude will be of this, and we will create a 1 lakh points from this. And the radius of this result should be this. This will be default if you don't provide anything else. So this is our all the functions we implemented, and let's try to run this. Uh, so here we enter a longitude. Let's say we have a 72 longitude and latitude, 18 point something 96, let's say. So let's find at least three nearest neighbors. Radius of 0.05. Let's say, yeah. As you see, the two CSV files are created, and here is our result. Here is the nearest find. This is the distance 0.700, which is the nearest to our points, and this is our radius, which is stored in CSV file. Now, if you have any question, please ask it.
Yeah. So, as you've shown, the average case performance is excellent, but what is the worst case performance for a KD tree, and under what conditions would it occur actually?
I would like to answer that question for you. That's a critical point. The worst case search performance for a KD tree is actually O of n time complexity, the same as a brute force search. This happens when the data is structured poorly or the query is pathological. For example, if we build a tree and then get a query that requires us to search both branches of the tree at almost every single level, we don't get to prune any branches. This effectively forces us to visit almost every node. A common cause is if the data points are not well distributed, but are perhaps clustered among a diagonal line, which makes it hard for the tree to make good splits. However, for randomly or uniformly distributed data, like our test case, the tree remains balanced and gives us that O of log n time complexity average performance, which is why it is so effective in practice. Any more
Um,
questions?
I have a question. Um, you specifically chose a KD tree, and why? Did you not consider any other spatial data structure like a quad tree or an R tree in your implementation?
Okay, so let me answer your question. So yeah, we did consider those. A quad tree is another excellent choice, which works by recursively dividing 2D region into four equal quadrants. It's very intuitive, but it can become inefficient if the data is clustered. You might have one quadrant with 1,000 points and another with only two, requiring deep unbalanced recursion. So our KD tree avoids this by partitioning at a median of the data itself, not at an arbitrary geometric center. This helps keeps the tree more balanced regardless of how the data is clustered. So yeah, R tree are also more complex and are typically used in databases. They are grouped nearby objects into a minimum bounding rectangles. R trees are fantastic for indexing, shapes, and regions. So yeah, it works very well. Since our project is focused on a static set of points and a pure search speed, the KD tree offered the best balance of high performance and implementation simplicity.
Any more
Okay.
questions, guys?
Yeah, just one last question. That in your implementation of code, you use your run medium select functions before building each node. Why go through that trouble? I mean, why not just fully sort the array by longitude, pick the middle, and then fully sort by latitude, and so on? Like, you understand that?
Yeah. So that's a great question about the implementation. Building the tree is a very what should I say, an expensive cost, but a one-time cost. So if we use like a full sorting algorithm like Q sort, which is a O of n or O of log n time complexity at every level of the tree, the total build time would be very slow, around O of n or O of log square n. So by using run median select, which is based on the quick select algorithm. We only find the median element, which is an O of n time complexity operation on average, which we don't care about the sorting and the rest of the data. The median finding approach is the much faster approach, reducing the total build time for the tree to O of n or O of log n, a time complexity. For a dataset with a million points, this is a significant performance saving during the initial setup.
So, any more questions?
Nah, I guess
I
we're
think
done.
that
Thank you
concludes.
for your presentation,
Okay, okay.
actually.
So
Okay,
maybe
so
this
that concludes the
concludes our
presentation.
It was a very
Presentation.
interesting project. Thank you for the presentation, and I think with this
this
we
concludes
conclude our
our
podcast. I
podcast.
believe.
Yeah.
Yeah.
Yes.
Thank you. Thank you,
Thank you,
guys.
everyone.